Good afternoon, everyone. I am Pamuthuransik. Today I am going to talk about interesting topic in artificial intelligence and audio processing, hybrid transformers for music source separation. This paper was written by researchers at Meta. This is the outline of this presentation. First, introduction, related work, model architecture, followed by a small demo, dataset preparation, experimental setup, results, and conclusion. First, the introduction. What is music source separation? Music source separation is the process of isolating individual sound sources from a mixed audio signal. Mathematically, we can interpret a signal as a combination of n different sources. That is what I have shown in this equation. Think of it like the music you hear, represent as yt, is actually a mix of several individual sound sources xt, where n is the number of sources. Our goal is to take the mixed signal yt and recover one or more of the xt signals. Depending on the music source separation system, the separated sources will vary. In this research, the mixed signals were separated into drums, bass, vocals, and other components. Let's talk about why it is important and how it is used in real-world applications. Music source separation allows musicians to isolate instruments for practice. For DJs and music producers, they can extract instruments or vocals to create remixes, mashups without needing the original studio recordings. And music source separation enables karaoke by removing vocals from songs. Beyond music, music source separation is used in speech recognition. In noisy environments like call centers or public spaces, music source separation helps isolate voices from background noise. Lastly, by music source separation, listeners can customize their music experience. This allows users to adjust the balance of instruments and vocals to suit their personal preferences. Next, we will see why music source separation is important. Now let's discuss why it is challenging. In a song, multiple instruments overlap in the time domain as well as the frequency domain. In the time domain, it is difficult to separate sources or even determine which instruments are contributing at a given time. In the frequency domain, there is more visual separation. You can see in this image, mostly vocals are concentrated in the lower frequency bands. Drums cover the entire frequency spectrum, while bass vocals are primarily in the lower frequency range. One of the most challenging instruments to separate is the flute. In visual domain, in the image on the right, objects in the image are clearly separable, but in the audio, it is not the case. Because of this, creating dataset for supervised learning in music source separation is also a tedious and complex task. Let's look at the different methods used to separate audio sources. First, spectrogram-based method. This approach works by converting the audio signal into a spectrogram, which represents sounds in terms of frequency over time, much like an image. The short-time Fourier transform is used for this conversion. Since different instruments have distinct frequency patterns, deep learning models can leverage these patterns for source separation. However, short-time Fourier transform is not perfect. The conversion can introduce some distortions to the converted signal. Next, waveform-based methods. This method directly processes the raw waveform. It captures fine details of the sound, but it is more challenging because raw waveforms lack clear visual patterns like spectrogram. Additionally, waveform-based processing requires handling a large amount of data. For example, with the 44 kilohertz signal, there are 44,000 data points per sequence to process. Despite this, modern deep learning models prefer waveform-based methods because there is no intermediate at conversions, and because computational power is no longer a major limitation, especially compared to the resources used for large language models. Next, one of the key reference datasets used for music source separation is the MuseDB18 dataset. It consists of 150 songs with 87 used for training. The music mixture in this dataset is divided into four components: vocals, drums, bass, and other instruments. As I described earlier, this dataset is comparatively small compared to datasets used in other deep learning tasks because of the difficulty of creating such datasets. Next, to evaluate how well on music source separation models perform, researchers use signal to distortion ratio metric (SDR). SDR measures how much of the desired signal remains after separation compared to unwanted noise or distortions. In the visualization I added here, if the predicted signal in the dashed line closely aligned with the original signal in the solid line, in this scenario SDR is high, meaning good separation quality. If there is a large difference between predicted and original signal, SDR is low, indicating poor separation with more noise and artifacts. Let's explore how models progress from spectrogram-based methods to waveform and hybrid approaches. We begin with spectrogram-based methods, which operates in the time-frequency domain. These approaches laid the groundwork for music source separation by using the rich information contained in the spectrograms. Two notable examples stand out: Open Unmix. This model uses a three-layer bidirectional LSTM network to predict magnitude spectrums of target sources. Splitter, a unit architecture trained on a massive dataset of 25,000 song extracts. It is its ability to separate audio components with high precision made it a game changer in this field. Next, look on waveform-based innovations. These models operate directly on raw audio signals, bypassing the need for spectrogram transformations. Let's look at a few pioneering examples. Wave Unit. This model adapted the unit architecture. And another one is ConTaskNet. ConTaskNet introduced a learnable front end to transform input waveforms into high-dimensional representation by using 1D convolutions. Hybrid method, the best of both worlds, recognizing the strength of both spectrogram and waveform approaches. Band split RNA, a new benchmark. Another exciting development is the band split RNA. This model employs multiple dual path RNA, each operate on carefully crafted frequency bands. By splitting the input spectrogram into subbands and processing each with desired RNN, hybrid debugs, and spare hybrid transformer debugs. These models are the core of today's presentation. This slide provides a comprehensive review of existing models used for music source separation, evaluated based on signal to distortion ratio metric. A higher SDR indicates better model performance. As I described earlier, the original MuseDB dataset offered limited training data, only 87 songs, with the remaining songs reserved for testing. To overcome this limitation, researchers added additional training data while developing their models and used the same MuseDB testing dataset for evaluation. The evaluation results are shown there. Additional training data, but the same testing data. In this slide, I categorize models according to the amount of extra training data used to train models. Blue, no additional training data. Green, up to 800 additional songs. Yellow, more than 1,500 additional songs. These are the key observations. Models trained with additional data consistently showed improved performance. However, the quantity alone was not the sole factor. Quality and the curation of data significantly influence outcomes. The band-split RNN model demonstrated remarkable performance even without additional training data, achieving an SDR of 8.24 decibel. After fine-tuned with 1,750 songs, its performance further improved by 0.66 decibel. The model we look at hybrid transformer demands trained with 800 additional songs delivered a robust signal to distortion ratio of 9.20 decibel, which significantly exceed the performance of other models. Next, architectures. Our main focus of this paper is hybrid transformer DeMux model. DeMux means deep extractor for music sources. Before going there are two other models, DeMux and hybrid DeMux, then followed by hybrid transformer DeMux. Let's briefly look at DeMux model. DeMux briefly processes the raw time domain signal. The model follows an encoder-decoder unit architecture with skip connections that pass low-level details directly from the encoder to, to the corresponding decoder layers. After the encoder, the network includes a bidirectional LSTM layer that captures long-range temporal dependencies. Before the decoder reconstructs separated sources. After the encoder, the network includes a bidirectional LSTM layer that captures long-range temporal dependencies before the decoder reconstructs the separated source. The model received a stereo audio mixture at the sample rate of 44.1 kHz audio length of 7.8 seconds. It outputs separate waveforms corresponding to the individual sources of drums, bass, vocals, and other instruments. Let's look at the encoder block works. In the figure, C in means the number of input channels and C out means the number of output channels. Each encoder block applies a convolution with a fixed kernel size of 8 and stride of 4 to reduce the temporal resolution. The number of channels is increased at each block. 1D convolutions and gated linear unit GLU activations followed before passes features to the next encoder block. After the encode, the compressed representation is fed into bidirectional LSTM layer. Then the information follows to the decoder. The decoder mirrors the encoder. Each block uses transpose convolutions to upsample the feature map back to the original resolution. In the final layer, a linear transformation without activation function is used to synthesize the separated waveform for all four sources. Hybrid DeMux architecture extend original DeMux by adding a spectrogram domain branch complementing time domain branch. While original DeMux processes the mixture entirely in waveform space, hybrid DeMux simultaneously leverage a 2D unit in frequency domain and then match both outputs. This dual domain strategy typically achieved higher separation quality, but at the cost of greater model complexity and computation. To further explain the changes made from DeMux to hybrid DeMux, I have summarized them. First, the original DeMux processes audio solely in the time domain, and hybrid DeMux added the frequency domain branch. Next, regarding architecture, the original DMUX used a single unit with temporal convolutions. Hybrid DMUX, however, uses two parallel units. In hybrid DMUX, skip connections are also applied to both branches. Finally, in terms of output formation, the original DMUX directly reconstructs the waveform. Hybrid DMUX, on the other hand, takes the output from the time domain branch and adds it to the inverse short time Fourier transform signal of the spectrogram branch. Next, hybrid transformer DMUX is an evaluation of the hybrid DMUX model for audio source separation. This model also have a time domain unit that operates directly on waveform and a spectrogram domain unit that operates on short time Fourier transform magnitude of complex spectrum. There is no change in the encoder and decoder blocks. In time domain encoder, a standard unit style block of four 1D convolution blocks. In a spectrogram domain, a unit style stack of four 2D convolution blocks. After these four convolution layers in each branch, the shape of the original hybrid transformer was carefully aligned so the time domain representation and the frequency domain representation could be summed. The main novelty of this architecture lies on the cross-domain transformer encoder. Next, let's discuss how it is achieved. Shared cross-domain transformer encoder. At the deepest part of the model, the time domain features and spectrogram features are processed in parallel by sequence of self-attention and cross-attention blocks. Self-attention layers operate within each domain independently. Cross-attention layers allow each domain to attend to the other domain's features. Positional encoding are added to the time and frequency axes. 1D encoding for the waveform features, 2D encoding for the spectrogram feature, then flattened into a sequence. Layer normalization is also applied for training stability, and layer scale is used to control residual connections by scaling residual connections to prevent instability. By interleaving self-attention and cross-attention, the model learns how to combine time and frequency domain more globally and flexibly than a pure convolution approach. This is a small demonstration of how these models work. The code is publicly available on the GitHub with train weights. Anyone can recreate the results. I was able to run this on Google Colab. Let's see the output. I will play the audio mixture.
Happy birthday to you. Happy birthday to you. Happy birthday to you.
Then I will play the extracted vocals.
Happy birthday to you. Happy birthday to you. Happy birthday to
Yes, you can see there is a good separation of vocals. And let me play the drums. There is no drums part actually. So let me play the bass. Yes, this is the component, and next the other component. Mostly instruments are in the other component. Next I have selected a song with more music. So next, dataset preparation. The researchers used additional 800 songs for train their models. Let's see how they curated the datasets. They started with 3,500 songs from 200 artists across diverse genres. Each song had stems labeled by producers, but these labels were noisy and ambiguous. They retained only tracks where all four sources, vocal, drums, bass, and other, were non-silent for at least 30% of the track. This reduced the dataset by around 1,500 tracks. They manually verified 150 tracks to ensure correct label. They found out it is tedious and time consuming. I will explain the next two steps more clearly in the next slide. From the manually curated dataset of 150 songs and MuseDB dataset, they trained their first version of hybrid transformer demugs model. Then their next step was to figuring out clean samples from the noisy set of data. What they did was they took a single song and parsed each stem separately, vocals, drums, bass, and other, rather than passing the mixed signal. The model then provides the output for categories. Ideally, for example, when only the vocal stem is passed, the output for drums, bass, and other should be zero, meaning no there should no sound be present on those categories. By passing one step at a time, they generated a p-metric. For a song to be accepted, the diagonal elements of this matrix should be at least 70%. Finally, they left with clean 800 songs for further train the model. Now there is an equation VZ. This equation is used to identify the signal energy in the waveform domain. These percentages are calculated based on this equation. They use 1 second interval and calculate V values and identify what is the step, what is the label uh, of those windows. All experiments were conducted on 8 NVIDIA V100 GPUs, each with 32 GB of memory. They use floating point 32 precision for all computations, ensuring high accuracy in model training. They applied L1 loss on the waveforms and Adam optimization. The model was trained for 1,200 epochs with 800 batches for epoch. The input to the model was the mixed audio files, which were sampled at 44.1 kHz, and they were stereo format. For validation, they used 8 additional songs. The researchers claim that while using a separate model for each source can improve performance, but it adds computational overhead. For a single pass, the model can process 12.2 seconds of audio. To process an entire song smoothly, researchers followed a structured step-by-step approach. First, researchers divided the audio into equal length chunks. Each chunk has a set duration, matching the length used during training. At this stage, these chunks are positioned without any overlap. Next, 25% overlap is introduced. Instead of placing each chunk directly after the previous one, it is shifted backwards by 25% of its duration. This creates overlapping regions. Then a linear crossfade is applied in the overlapping region. In this process, as the transition progresses, the first chunk's contribution gradually decreases from 100 to 0. Simultaneously, the second chunk's contribution gradually increases from 0 to 100%. This approach creates seamless transition, preventing abrupt changes that could introduce audio artifacts. As shown in this here, hybrid transformer debug model with spare connections achieve best overall signal to distortion ratio of 9.20 decibel, demonstrating superior performance across categories. The researchers were able to increase the overall performance by 1.56 decibel in SDR compared to baseline model. Meanwhile, the band-split RNN model remains highly competitive, notable excelling in the other category with 7.08 and vocals with 10.47 decibel, despite using a fundamentally different architectural approach. In this study, researchers analyzed how three architectural hyperparameters influence model performance, as presented here. These hyperparameters are duration of the audio, depth of transformer encoder, and dimension, which refers to the internal size of feature vectors in the transformer encoder. It is important to note that increase in the duration of the audio segments does not increase the number of parameters in the model. However, it significantly increases the memory requirement due to attention mechanism, leading to out-of-memory issues. They also measure real-time factor, which indicates how quickly model process audio. When, when the input duration of the audio increases, the RTF value also increases, since long audio segments provide more data that need to be processed. Overall, the best performing configuration was the architecture of duration 7.8 seconds, depth of 5, and transformer encode dimension of 5 to 8. This configuration provided the optimal balance, maximizing SDR performance without causing memory issues. Let's quickly highlight the key takeaways from this result. Using longer training generally gives us better performance, but there's a limit. We have to keep an eye on computational resources. Going deeper with the transformer can boost performance too, but it is important to find out right balance so we don't run into memory issues. Increasing the dimension of the transformer encoder helps a bit, but these improvements are small. So sometimes the extra computational cost might not be worth it. Now let's discuss two important data augmentation techniques, remixing and remixing, and their impact of model performance. First, remixing. It involves recombining the individual tracks or stems from different sources during training. For example, the vocals from one song might be combined with comes from another. Next, repitching. Repitching changes the pitch and tempo of audio tracks. For instance, a song might be speed up or slowed down during training. Looking at the results, it shows that remixing remains highly important for training the model. On the other hand, repitching has a smaller impact, but remixing is essential to achieve and maintain high performance. Next, the researchers conducted a series of experiments to evaluate the performance of the model under different configurations. The model parameters were fixed in those experiments. The initial model achieved an SDR of 8.80 decibels. By incorporating spare kernels, the XDR improved by 0.14 decibel, reaching 8.94 decibel. Fine-tuning the model on a per source basis further enhanced by SDR by 0.2 decibel. An attempt was made to extend the receptive field of the transformer encoder to 15 seconds by reducing the batch size. An attempt was made to extend the receptive field of the transformer encoder to 15 seconds by reducing the batch size, because longer input sequences require more memory. However, this did not yield additional improvements as the SDR remains at 9.20 decibel. Next, finally, these are the potential improvements that I have come up with. First, knowledge distillation. We can leverage knowledge distillation to compress this model into smaller, more efficient ones. This is particularly important for real-time applications where computational resource might be limited. Next, unsupervised or weakly supervised learning. This kind of learning method is good because the number of client supervised audio data is limited in this problem. Models like recent wave-to-wave demonstrate how models can learn robust representation from unlabeled data. I would like to discuss in brief key insight from hybrid transformer DMARC model that applied in modern deep learning architectures. Hybrid transformer DMARCs illustrate how combining convolution layers with attention-based transformers. Similar cross-domain or multi-model fusion approaches are increasingly common in generative AI, where we merge different data representations, text, images, and audio. Hybrid transformer DMARC uses self-attention to analyze sequential data, which inspires similar methods in vision, where images are processed as patches instead of full grids. Thank you for your time and attention. I would be happy to answer any questions you may have. Thank you for your time and attention. I would be happy to answer any questions you may have.